from INTERSTORES project. Michael, the floor is yours.
Thank you very much for introduction. I don't know if you can see my screen.
Yes, we do.
Okay, perfect. I will start. So today I'm going to talk about the development of a reduced order model for seasonal thermal energy storages, which is part of the INTERSTORES project. If you're interested in the project itself, you can scan this QR code. It will direct you to the homepage. And I will show you some results of our recently published paper. If you're interested in the paper, you can find the link here. So what is the motivation behind this? This is part of INTERSTORES, and INTERSTORES itself brings together 14 partners in 9 different countries, and it focuses on optimizing and implementing seasonal thermal energy storage at 2 demo sites. One demo site is the InCampus in Ingolstadt. It's a gravel pit, and the Varanto cavern storage in Finland with a size of like 1 million cubic meters, which would be the biggest cavern storage so far. And one aspect of us from HSLU was the development of a reduced order model in Modelica, which is both fast and accurate, so it can be then used for system simulations in real environment. So the issue so far was that we don't have measurement data yet, so we had to come up with a process how to create this ROM. Therefore, we used a validated COMSOL model created by AIT, which is one of the project partners. And the issue with this one is that it's rather detailed and quite computationally intensive, and therefore it's impractical for the real-time system simulation. And to address this, we created the reduced order model in Modelica. So how did we proceed? We defined similar input parameters and boundary conditions, which were then fed into the COMSOL multiphysics model, which then created results. Parallel, we created the reduced order model in Modelica and then did the calibration process in order to match the results from COMSOL and have something fast, which is suitable for like digital twinning. Here you can see the key design parameters which we used. So the parameters has like different size variation. We made simulations from 20,000 up to 200,000 cubic meters with the given parameter here in the list for like soil and fluid and so on. The simulation itself, we made 5 complete annual cycles, where one cycle is represented by 90 days of charging, 90 days of storing, 90 days of discharging, and 90 days of idle phase. In total, we make 5-year simulation, and for comparison of the results, we use the 5th year. Here you can get a quick insight on the COMSOL model which was used. It's the De Plates model developed by AIT. And this is supported by the finite element method, and it includes multiple features. So you can simulate all kinds of different sTES systems with it. And for this study, we focused on a water-based system without groundwater flow in the soil. This is the reduced order model we created within Modelica. It mainly consists out of 3 components. One is like the stratified tank model, the second one is the buoyancy model, and the third one is the ground model. Both the stratified tank and the buoyancy model were based on the buildings library, and we made strong modifications. So in order to first represent the proper shapes, in our case for this study the truncated pyramid, but the model itself can represent from cone to pyramids to cylinder, basically all kinds of shape. We used for this equidistant discretization. For the study, we used 200 layers within the tanks, and you're able to connect basically each layer of the tank with in and out flow connections. Then for the ground model, we created a 2D grid with finite volume method, where each element represented by a 4R1C network to simulate the interactions between the ground and the tank. Here you can see results we got from this study. The thermal losses from the tank itself, particularly for the uninsulated variations are shown here. We also did simulations for the insulated, but the difference are marginal in this case. So as you can see in this chart, the side losses play a dominant role, especially as the size decreases. For large tanks, the side losses are roughly 50% of the total losses, and for smaller tanks, those increase to up to 66% due to the higher surface volume ratio. Bottom losses in total are the smallest contribution overall, sizes ranging between somewhere 7 and 9% of the total losses. Even though we have slight disagreements, the overall alignment between the Modelica model and the COMSOL results stay in an acceptable range, somewhere between 1% and minus 2.5%. Here you can see the temperature profiles for the different sTES size from 20,000 to 200,000, representing 5 relative heights within the storage. So where 95 is the layer close to the lid, and the 5% represents close to the bottom of the storage. So you can see quite close alignment, especially during the constant conditions, but as soon as dynamic events occur, the temperature profiles from the two models show minor deviations. For example, during charging, the Modelica model initially underestimates the temperature slightly, but once it continues, it slightly overestimates by 1 Kelvin. Those differences are largely due to solver settings and the different discretization methods used. So the COMSOL model uses like advanced solvers and integrating the energy balance equation over the entire discretization element, but Daimler, for example, exports the temperature data at the center of each cell corresponding to a relative height and follows a nodal approach. Here you can see the root mean square error distribution of the 5 chosen layers. The deviation between COMSOL and Modelica were on average somewhere between 1.2 and 2.4 Kelvin across the different layers, and this level of accuracy basically underscores the robustness of our model. Although there is still slight room for improvement, for example, in extreme cases when the tank is very small or rather very big. What's also to mention here, as you can see, best performer is the 100,000 cubic storage, but this is based because we started with this one and all the calibration and validation was done with this, and then we scaled it up and scaled it down. If we take a look at the energy balance, you can see that the Modelica model consistently underestimates both the charged and the discharge energy compared to COMSOL by roughly 5%, but this is also mainly due to temperature evaluation inside the tank. So smaller storages basically have higher surface to volume ratio, and in these cases the thermal losses are more dominant and the stratification is less important. But for larger systems, they have stronger thermal gradients and more strong stratification, especially near the inlets and the tank bottom. So the COMSOL model itself captures those behaviors by using a fine mesh and a fully coupled physics, but the reduced order model employs a simplified layer-based structure and buoyancy treatment. So as a result, small temperature mismatches can accumulate into more noticeable deviations as if the simulation time is longer. For the computational time, here you can see the comparison between Daimler and COMSOL. So we optimized the reduced order model by calibrating the segment count based on convergence tests to ensure a stable stratification without excessive runtime. So in COMSOL multiphysics, there is a direct fully coupled approach with the adaptive mesh refinement and by use of the MUMS solver. And in Daimler, we used the Dussel solver, and we ranged time steps between 10 minutes and 1 day. For both comparison, we used the same machine, and we were able to reduce the simulation time by up to 98%. Which already brings me to the conclusion. So the reduced order model has demonstrated strong performance, achieving deviations of less than 2% in temperature simulation. And during the calibration against COMSOL simulation, the model was, let's say, highly efficient, and we were able to complete a full year simulation in roughly 4 seconds. I mean, for example, if we simulate something like Dronninglund, which is highly complex, then it increases. But for example, annual simulation for Dronninglund, we still manage with roughly 1 minute simulation time. What are we now planning to do? So first of all, we already did the FMU export, and we are about to perform some parameter calibration with FMPy. And then additionally, we will working on different storage media, for example, the gravel water mix. And then, which is also ongoing, is like model refactoring, so we can make it accessible to other person and more usable. Ultimate goal at the end is then to implement this one in an MPC and then install it on one or both of the demo sites once they start operating. Thank you very much.
Thank you very much.